last time we have learned the definitions. First, the definition on a nonlinear step polymerization. What's the difference between the regular step polymerization, the linear one, and the nonlinear one? Okay, what's the difference between those two? And then we now look at some examples. We are in the commercialized name is the backlight, if you remember, okay? The backlight or backlight. So backlight or backlight. Okay. So basically, it's formaldehyde-based resins. So of course, it is going to have two components to make this backlight. So I think also last week we discussed on how the benzene rings, they have the sites that is going to be active, okay? And we know that it will be active in the 2, 4, 6 positions, as we see from the picture. It will later connect to the other substituent, okay? And then we are going to see that after the reaction or upon reactions, we will see the methanol, the methyl and the alcohol. And we have seen that if this is going to later react, okay, this methanol, it will going to, for example, if this is going to react, there will be two processes. Okay. First, it will just normal methylene bridge like this, or we have with links with the ether, okay? The dimethylene ether. So we have an oxygen in between of this carbon. Okay. So this is just two possible route for the formations, and there are also other example, which is we call this nofalax. This is we prepared the excess of phenol, and we add the acid catalyst. We add the acid catalyst to promote the condensation of metal. So we have this methanol going to be condensed. Okay? It's going to be condensed. There are other, I forgot to mention, there are other also, it's called the resols, that is with base catalyst. So we call this, the other ones resols. This is prepared. By excess of formaldehyde with base catalyst and because it is excess on the formaldehyde, then there will be some unreacted methanol, which we are going to see on these results. So normally this nofalax will be, let me just add, they will be dried and ground to powder. So it's going to be like in a powder state, and then we add fillers, and then add fillers like glass fibers, mica glass, okay, and then add colorant and hardeners. So during this step, we can add as much the component we want. We can harden the powder. We can add color. Okay. And of course, this fillers is going to improve some property. Okay. So we can adjust the mechanical property, we can adjust the electrical also property. And then later we are going to react this with the hardeners. The hardeners usually the hexamethylene. Hardener is hexamethylene tetraamine. Okay, that's just a wrap up the last week, this one. And do we have another one? Oh yeah, we have another one that is the chemistry of the urea formaldehyde. So as you see from here, so let me just rephrase this. This is just an example. Okay. So chemistry of urea formaldehyde and melamine formaldehyde involves formation and condensation reaction of the N methyl groups. Okay. The reaction usually arrested at pre-polymer stage by adjusting pH. So if it's basically quite simple. If we adjust the pH, base or acidity, we can make the polymer hibernate, like a hibernate. Okay. So if we change the pH, we can make the polymers prepare to be reacted. Okay, prepare to be reacted. So if we want to make slip, we are going to take the pH as alkaline, well, slightly alkaline. This is hibernate or arrested. And then, as usual, we can blend these pre-polymers or pre-polymers. Can be adding the or let me write blending. Can be with fillers like colors, okay, colorant, hardener, okay, and others if we have, if we can. Okay. And the hardeners, usually the hardeners is ammonium sulfamate. That will react, and of course it will give acid, and it will be condensed into this long chain polymer. But I think if you remember the basis for this bakelite, okay, you can think the bakelite as a, let me write what you need to know. I mean the basic. If you see a lot of these polymers, maybe confusing if you see the terms. Let me just remind you what this does it mean in this formaldehyde and resins. Okay. So we are going to have formaldehyde, and let's say we have a phenol. Okay. The basis is these two. So the formaldehyde and this phenol here. Basically, it will attract this carbon. Remember that it starts to be the active site, or we could say nucleophile. Nucleophile reactive. So the electron will attack this carbon, and later this oxygen on phenol, this will also attract it, and then because we have a benzene here, remember that it will activate the 3 position on this benzene, right? And later that positions will polymerize, or we could say it will prepare the compounds to make an active site for polymerization, or maybe we could say just it's going to react with other substance. And remember that in this phenol we call this mesomeric structure. Okay. That we see that the electron later can shift around. So from this part going here, and going there, and going there. So because of the unstable on this oxygen, then to stabilize itself, it's going to be shifted around. And we call this benzene is a mesomeric structure. And then you'll see that because we have the hydroxide, okay, on this phenol, then it depends on what we are going to achieve. We can take the base catalyst or acid catalyst, and then based on that, we can make the formaldehyde more or the phenol is more. Okay? It depends on the reaction, depends on how the environment. So it can be done both environment. Okay? And we call, I think in the previous slides, if we take the base catalyst, we call the resols. If we take the acid catalyst, we call the non-volatile. But that is just an example. Okay, so this is the basics. Okay, the basics. Okay. Now, what else do we have? Oh, we have some movie. Just a few seconds. Let me. I forgot to mention. Wait. Here. I think here. Take that. Okay, and then this is epoxy resins. So we'll see there will be some natrium and hydroxide. There is a change on that side there, and make a new bond there, and then take away the hydrogen. Okay, and then with the natrium, it brings another. That's the epoxide. Yeah, the epoxide. That has this triangle here, okay? And that's what we are going to see. So this is the pre-polymer. So we are going to see this is how to prepare the pre-polymer, which is we have this epoxide. Okay? And the key on this epoxy resin is to make the epoxy, which means the epoxide going to be break. Okay? The triangle here is going to be break. Okay. Okay. And then let me go for the other one. After the pre-polymer, then we move to the hardener. Okay. The hardener usually it has the amine group that we're going to break down those epoxide. Let me go one more time, or maybe let me go to. Okay, so the amine group is coming. So and it has some electron. This is more reactive. Goes here, and then this is going to stabilize itself. Okay, and then later will be polymerized. That is basically what we are going to see in every, I think, in every typical cross-linking. This is, I think, very, very descriptive. So let me go here. The epoxy, let me write, I think, let me write some of the applications. So usually we are going to have a two component. As you can see, we have this pre-polymer, right? Or we call the resin, and we call the other part is the hardener. So we have the resin or the pre-polymer and hardener. And it's worked like a glue. Okay? So the hardener is worked like a glue. So it will glue all the pre-polymer and make them bind each other. So it is, let me write, a strongly bind to a lot of substance. And it has a long shelf life. And as a composite materials, we can think like maybe like a fiber plus the composite that we are going to see. This is going to result in high mechanical property or stability, which means what I mean here is if we want to make a composite materials, okay, we can prepare, for example, like a fibers, and we can make a composite through these resins, and then we can adjust the mechanical property. For example, if we want to make something strong in terms of composite, we can add the fibers inside the composite. So perhaps this is the fiber, right? But if we just have the fiber, then maybe it's not really useful if we have this fiber like that. But perhaps if we make it, connect them all together, binds all together, and then makes them in a precise way that is going to be have like something that is mold, and then they will be formed together. Then we can make a composite, okay? Then this composite can be think through this epoxy resins, okay? So if we take resins, we fill with the fiber or other material as well, we can make maybe something stable, something strong enough, like the formaldehyde before. We can add glass, we can add another materials, okay? And then we cross-link the polymers all together with the fibers inside, and it would be maybe very useful, maybe, probably for protections, or maybe making something in a like in a table like this, okay, chair. Okay. I think most table is from the woods, but the composite woods. Okay, it's like a layer, but different with different directions, or we call the different isotropic materials. If you remember the material property, if we combine all together, in the resultant on the force, it's going to be quite good, quite stable. The same thing with the fiber here. Maybe the first layer like this, second layer maybe going to be like this, the fiber, and then put all together again like that, and maybe after that we put them together, maybe this direction, this direction, this direction, this direction. Maybe we can make something strong. Okay? Because these directions, remember, if the fiber, they have strong uniaxial strength in this direction, right? The fiber, and that's how they design the Kevlar or the armor with the fiber. Okay, so this film before is to prepare the pre-polymer. So not really important for our course, but the most important one is when we have the epoxy, the triangle. The important thing is we know why it's going to be broken down and how to polymerize the hardeners inside. So let me move to the next one here. So the hardener, so this is the epoxide. So this is the epoxide, this is the epoxide. Okay. This is what we are going to focus. Okay. So whenever we move on into some different examples, if you think like this other components, compounds, elements is too much, focus just one thing. Okay? For this case, we focus only on this triangle, and just focus on this. The later part is, well, it's important, but not as important as this one. Okay? This one you can look at your book, look at your reference, but this one you need to understand. You need to understand the principle first. So the epoxide, it tends to open. Okay, so this one it tends to open. Okay, so let me write, tends to open up. Do you know why? Because look at the electron. It has 4 electrons here. So already dense. Locality of electrons is already higher on that positions. So we can say at the these positions, perhaps here, this is going to be prone to a nucleophilic attack. So we can say that this triangle is actually unstable. So for the industry to prepare this kind of epoxide, then they need to make the pre-polymer that has this unstable. Okay, now if we look at some example here, again, maybe if you want to write, you can write first here, the epoxide. It tends to open, the carbon is prone to nucleophilic attack, And as you maybe look at the video before, we see the natrium hydroxide, right? Which means it's basic, right? So the catalyst, we are going to involve the base catalyst, which is the hydroxide groups, that will help the reactions. Because we can see also in the example here, we are going to see this is an example using the bisphenol A and epichlorohydrin, which is we take this natrium hydroxide. What we can see is we are going to take it as a polymerization based long reactions. So let me start with the let me check first. Okay, do we have the space? I think okay, this is the formal reaction. So let me write in more detail on the electrons. Take okay. So let's say this is the so let's say we have the bisphenol like this, right? I mean, I'm just writing the important one here. So this bisphenol here, and we have that. And then after we take this, we have the base, or we can say the hydroxide groups. Or if you want to make sure that this is going to be in general, what we have is actually maybe with green. In general, we have the HOROH. So R can be anything and can be this bisphenol. The difference is probably how the electron will localize, how much electron will be localized. Or probably the other difference is the rigidity. Okay, the rigidity, if we have the bisphenol, like the phenol group inside, I mean the benzene, it's more rigid, right? It's more rigid, it's more not flexible, right? So if we take this, or maybe take this example with ORO, we take this as the electron that is unpaired for the oxygen, and it will attack this part, right? Attack this part, one part on the epoxide. So let's just seems that this attack like that, and then these bonds will move out. So let me write what will be the Cl, H2C, CH, CH2O, R, O, and then this O also, the other side, this one also, do the same thing and attack the other part, and this will also make another one. And this will be, I forgot the oxygen here, right? Let's check. Okay. And then again, this oxygen have this electron, and both sides will stabilize itself. So the electron will stabilize itself. It's also stabilized itself, which means that this chlorine bond will also broke. Okay, will also broke, and then we see that this chlorine will get into the natrium that is in the first phase on the hydroxide. So it has the hydroxide groups, and also we have the natrium, right? The natrium will make out with the chlorine. But this will make double epoxide on both ends. Okay. So this will make another triangle. Okay, this will make another triangle, right? And this chlorine will be removed. So this is just a short polymer then, right? Short polymer. Do we want this? Do we want this short polymer? Where polymer should be long with short? This is really short polymer is like a contradictory terms. Right? It is short chain. Okay? So actually we don't want this. Okay, we don't want this. So the idea is then we need to make sure that only one side is going to be actively polymerized. Okay? So let me write here. This is short polymer. So short polymer with epoxide, right? And then we see that because it's short polymer, then we say that this polymer is not, or we don't want this, right? Or maybe they're not wanted. Then what should we do? Then first we need to add epoxide in excess. So we need to add more possibility for the epoxide, and then we need to have stoichiometric to make sure that all the components are they are proportional. Okay. So we need to add epoxide in excess. But anyway, this is pre-polymer. Okay, this is the pre-polymer. Let me write here the pre-polymer. That has the epoxide. Okay. Okay, and then we see the hardener. The hardener will take the amine functionality to take the reactions. Okay. So this first part is preparing the polymer, the resins, the epoxide. The second step is the hardener. Okay. If we see here, we have a typical hardener that is going to, if you see from these 4 components, we have the diethylene triamine or beta, theta, DDM, DDS. All this, okay, although they have differences, they have the same in common, that is the functional groups, the amine functionalities. Now the idea of this amine is to make this epoxide that we prepared before, we are going to break down this epoxide and then make sure that this nitrogen is reacting and make the reaction with this epoxide. Okay. So we call this process as a curing. Okay, so it's the process curing, and then it will be a polyaddition reaction, okay, with the epoxide groups. And of course, the chain length of this amine R group and the resins, it will control the mechanical property. So we can make sure, for example, this R, if you make more rigid, and maybe like the benzene here, maybe if you have some benzene here in the middle, and also in the epoxide, this carbon here, if we make maybe more rigid, maybe this will be more having stability is more, strength is maybe higher. Okay. Or if we choose to make it more flexible, then maybe just aliphatic chain, okay, for each R. So we can adjust the mechanical property in that. If we take, let me go back and then add the reaction for the hardener. Okay, so this is the hardener. So this is the amine. Okay, let me write just one side. Okay, and then add the epoxide. Of course, it starts from this nitrogen. It has a paired electron, and this is the same what I've told you before. So attacking this part here, okay, to make the bond broken, and then it will turns out it turns out to be like this. And since the oxygen is not stable, it has a lot of electrons that is localized, it will contact this hydrogen, okay, to make a friends with this hydrogen, and then it will be removed. Okay. So we are going to see that it will and then this nitrogen is more in negative now. And later we see that it will be react with this. So this is precisely the same as the previous picture. I mean, the N is attacking the epoxide. So there are other epoxide that is going to react with this nitrogen and make this four chain. And this amine functional groups, the more we have, if we take more, so the more we have, then it will be faster the solidification. Okay, so the idea is from this nitrogen attacking this site that is prone to nucleophilic attacks, and then open the triangle, and then the chain will comes up to the nitrogen. And it will goes through like this part here. And of course this H is going to be removed as well. I forgot to remove that. So it will be like this. So the epoxide, so it's attacked here, it's open, and then it goes inside, and it's make the OH here, OH, all the alcohols, okay, from the oxygen from the epoxide, and react with the hydrogen from the the amine. Yeah, the amine. So the F here, F equal 5, 4, 4, 6. That is the amine, okay, the functional groups that is inside the substance. The more we have, the faster the solidifications. But of course, there will be some pros and cons using for each these amine functional or hardener. Perhaps it's faster, but maybe you need to make sure that it's not too fast. Maybe because you have another fillers inside. But by default, but it is faster. We have like the more n. Okay, for example, this one here have the f equals 6, which means that is the fastest one. Okay, that's the basis on epoxy resins. Okay, another part is the polyurethane, what we call is a network polyurethane. Basically the same. Okay, basically the same. The difference is probably how we prepare the end groups. Okay? So we need to prepare the end group that has potential to be branched. Okay? The reaction is the same. as the original polyurethane. So we are going to have for example, the foam. We take the water, add the isocyanate, and then the same as the linear one, the same. And then it has the amine release, and it will react with another isocyanate to make the urea that is going to make up the polyurethane. And this is one example. Okay, we have the triol that is going to be reacted to make network with the isocyanate to make the network polyurethane. So the idea is just to make sure that it has branch. Before we have only diols, right? Only linear. Okay. So isocyanate and diisocyanate diols make a linear chain polyurethane long, right? And now we have 3 alcohols that we're going to react. Okay, I think we are ready. So we continue. So perhaps this is going to be the alcohol groups that will react with the diisocyanate or isocyanate. So this will plus with the isocyanates, and then it will react with and becomes the network polyurethane. And then to know how we react, how the molecular weight predictions, as we've done in characters, we also do the similar thing with the network polymers. We have the gelation theory. Okay, so this is coming from the same characters but with some modification. Okay, so let me just take some review on characters. Okay, what's the important thing on characters? So first, in characters, we can compute the degree of polymerization, which is the monomer divided by the monomer after some time. So after some process, right? How much is polymerized? Okay, so it's number of molecules at t equals 0, which means at the initiation, and number of molecules after some time. And then another important thing in the characters is the P, the conversion. Okay. P. We say the P as the reacted groups divided by initial groups. Remember that in characters, what we are going to see is how much the functional groups, okay, that is reacted. Other component is not significantly affected the reactions. Only the functional groups. Okay. I mean to multiply by 2 because we have functional groups. So 2 functional groups. Or right, 2 functional groups. So now if functional group is greater than 2, what will happen? Now we are going to discuss them. Okay. So we are going to see the same or similar idea from these characters, which is the degree of polymerization, the conversion, okay, the number of molecules. We are going to see all of that, but we are going to see when the functional group is greater than 2. That is the for nonlinear, right? For the network polymers. So we start from these two components. Okay, so consider 2 components. Okay? The previous one is the same as the character theory that you have learned last week. Okay? So imagine we have the A and B. Okay? So see this 3AA and 2B, and it has 3 functional groups. Okay? in the character theory, the normal one, we take the monomer both difunctional, right? AA, BB, that's the characters. But now in gelation theory, we have, for example, the B is 3 functional groups. Okay. Now, if we take this and then we need to define the average number for the functional groups, what we can do. Now, if we take back to what we have in this, okay, the reactor groups is this part, right? Or actually, we could write this as P and R, or at the end that is reacted, after some T multiplied by 2 divided by, we can also write like this, A, B at T0. So NR is the reacted molecules. Now in the character theory, we can write NAB at T equals 0 because A and B, it has the same number of functional groups. So we can write like that. Now the problem in the network polymers is the NAB is not equal with the N0 or the initial molecules. Okay, so here the NA NB is the same as the original molecules. Okay, so here, problem, let me write the problem first. The problem is the NA and NB is not equal to the initial molecules because F is greater than 2. Now we need to define the average number. Okay, so to make up the functional group that is 2 in the character theory, we need to define the average number. So rather than writing with so if we change the number, we would also change all the calculation, right? So the first thing is we need to define the average number. So the average number, F average, is by taking the sum of the number of molecules and number of functional groups and then divide by the number of molecules. For example, the average number for the one that is mentioned here for AB, okay. So F A B average, okay. The molecules 3 and 2 is 5, right? 5. Molecules A is 3, functional groups is 2. So 3 multiplied by 2. Okay. Functional groups B is 3, molecules is 2. So 2 molecules multiplied 3 functional groups. So this is for A, this is for B, right? For the average. So we take this and so 3 by 2 is 6, so 6 plus 6 is 12, so 12 by 5, 12 divided by 5. Or this is equal to 2.4, so this F average is 2.4. And we can also rewrite the NAB0 as the N0 multiplied with the F average. Okay, so we define this for our new terms in the future for the nonlinear polymers. And then the other is the NR, that's the same as before. This is the process, how much the molecules are polymerized. You can also read this NR as molecules that reacted, which means the initial molecules minus the molecules that in the left one. Okay? So molecules that polymerize. Okay, and then from this average number, let me just go to this part here. Okay, the average, the left one already we've done, and then we can write down this conversion, okay, the P conversion, the extent of reaction or the conversion at some time. So this number 2, this is coming from okay, let me rephrase this. Okay, if there are some initial molecules and N0 present at initial, then total number of functional groups has become this. This is the same as we mentioned before. If at time t there are n molecules present, then number of functional groups that have reacted is 2, because this 2 is at the most, that is at least two different molecules. At least two different molecules. This 2 is from A and B, right? Okay. Two different molecules that has the functional groups, in which the functional groups has their average. Okay. So we can rewrite the P as 2 multiplied with this subtraction between the initial molecules and the molecule left, or this is the molecules that has reacted, divided by the initial molecules and the functional group average, and then we can rewrite using the degree of polymerization. Remember that the degree of polymerization is related to the number of molecules. Okay, if you remember, the degree of polymerization is the initial molecules, and you have the molecules that is left after polymerization, and you need to know what's the ratio between two of them. That is the degree of polymerization. So the initial molecules, and then this is the molecules remaining. So where are the other molecules? It's polymerized. That's why it's called the degree of polymerization. So we can rewrite this xn, or degree of polymerization, here, and we can rewrite all of this. We make the degree of polymerization. Okay, so we have 2 over 2 minus Pf. And of course, from this degree of polymerizations, we have some limitation on the conversion and the average. If you let this equal to 2, then it will be 2 divided by 0, right? So it will be infinite. And in our computation, in our assumptions, if we want to make the polymerization as high as possible, which means we need to make the degree of polymerization as high as possible. So we need to make this part as high as possible, right? So if we take this in terms of limit getting close to 0, so that is what we want. So we need to know there is some limit for the speed that's going to be critical, and when it's crossing those numbers, the polymerization will be high. Okay, so we call that as the P critical, PC. Okay, so this is the P critical. So if we take this into our equations, we can make our polymers yields as high as possible. So we can polymerize our monomers more in high results. Okay. So we need to make, so P critical means that we need to make the xn, or the degree of polymerization, goes infinite in calculations. We call also this is a critical conversion. From the previous example, we have the F average is 2.4, right? So we can maybe example PC is 2 divided by 2.4. So when we have this PC, then we need to maybe take a little bit more, and then we make sure that okay, it's going to be polymerized completely, okay, and then it will be enormous result, a high result. Okay. If we take different values, if you look at the table, gel means it's going to connect all the network. Okay. So if we take the xn goes infinite, it means that this infinite means that we are going to connect. So let's say this is the chain. So we are going to connect all the chain with this branch point here, the gel point. And if this is completely polymerized, all the networks, we say the terms is gelled. This means the gel point is making a branch. So if we make more groups, functional groups, we increase the groups, like before we have A, B, if you take B, B is already 3. If you take B is 5 or 6, then more groups, then this 2.4 is increasing. So we are going to lowering the P critical, right? So we can also adjust the P critical as in the calculations. If you see the calculations, this is F average, okay? And this is the difference in the conversion, the P. If you see how does it affect the polymerizations, you see that when it's 0.5, okay, if we increase the F average, it not necessarily increase anything. But when we have the P as nearly as maybe from the 0.9, okay, we have 2.3 F average, it's getting gel, so it's getting completely polymerized. And when we have 0.95 at F average 2.2 is also gel. But when we have like a 0.99, okay, and we have the 2.1 F average, it's gel. So we need to make this connection between the P and F average. How is the optimizations? Okay, we can think maybe before this table, maybe we can think which monomer, okay, what kind of polymer do we want, and then also the cost, the productions, what kind of reactions we are going to need, okay. And then we can take some calculations to predict. This is and again, this is a prediction using the calculations, using the gelation theory. But there are some weakness too in these relations. Let me show you. But before that, there are some statistic theory of gelation. Okay. Wait. Okay. So perhaps going to this first before we move to the weakness of gelation theory. So there are some statistic theory of gelation. So the statistic theory, this is going to be focusing on this alpha. Okay. So alpha is, we call the branching coefficient. Okay. So through these calculations, we are going to see how is the probability that the branch will be made out from the polymer. Okay. That is the alpha. So we say that we have this general sequence. So AR, AB, RB, and then we focus on this AR, AB, RB. That is the repeat unit. And of course, from this general sequence, we can think the probability. First is probability of this chain, the left one. Okay. Left one here, this is the PA. Okay. We say the probability of this segment PA. Okay. And then we need another terms that is going to make out with the sequence, because we take the probability. You learned probability before in math. So if one is A, then the other one will be 1 minus something, right? So we need to make another terms that is G. G is the initial ratio of the A groups from RAF molecules to total number of A groups. So this G will be in the other terms of the PB, the BR, BA, RA. So this is another term that is going to, so it has a two sequence, okay? So two sequence. So this one here, but in terms of, or if you want to write, maybe you can write twice. The first one is going to be this. The second one is going to be, the first one going to be here, and then going to be that way. Okay? Yeah, I hope you get my point. It's because these two is this one, okay? And then the other one is this PA here, okay? And then the other part is BR. So here, BR, BA, RA from the right. Okay. So let me write for you. Okay. Let me write for you. So A, R, A, B, R, A, B, R, A, R, A, B, R, A, B, R, A, R. Okay. The same sequence, but I write from the right to the left. Okay, to see how it works. Okay. So that's PA. So this is the same PA, AR, AB, RB. So this is the same PA here. And then AR, AB, AR, AB, R, AR, AB, RB. Oh, wrong. A, BR, BR, BA, RA here. Okay, this is PB. And and this is PBG, and PB 1 minus G. Now the total probability is PA multiplied with the PB1 minus G, and then PA, the PA has repetitions, and then PBG. Okay. So this is probability of the sequence. Okay, that's the probability. And then the branching coefficient is given by this. Will be this sum reaction, summations of the repeat units. And then using the sum of the geometric series, if you remember, this 1 over 1 minus x. We can also relate the critical branching coefficient, the AC, as 1 over f minus 1. So it's from here, this 1 minus PAPB, 1 over 1 minus G. The same or similar condition with the P critical, we can also make the branching coefficient critical. Okay? So coefficient, critical branching coefficient. So this is, we are going to take, so the F will be we can deduct what can this F will be. And later we can take the critical for extent of reaction at gelation with both of this PA, PB, okay, and 1 over 1 plus G F minus 2. And we can rewrite in terms of PA or in terms of PB. Okay. R is the ratio, okay, of A groups to B groups. But I think the most important here is I think no need to write all these components. This one, okay, the branching critical, and this one. Okay, because I don't think all the things here can be can explain all things here. Okay, now back to this part here, the table. So what's the assumptions? So if we have this table, this table is reaction between diol, diacid, and triacid. So we have a variation in P, the conversion, Xn, the degree of polymerizations, and the viscosity. Okay, viscosity. Okay, now focus on this part here that has a dot line. Okay. This dot line that I write here, the dot line is the gelation, the prediction of gelation. It's going to be at this dot line. But if you see the viscosity, where does it end? It doesn't cross this dot line, right? It's supposed to cross that because we predict that there is gelation going on, but the viscosity, if we see that the curve is going to be infinite. So we can say, okay, what happened, right? So first is the assumption. So sometimes in this gelation theory, so let me write. So gelation theory is simple, but overestimate the P critical. Okay. So because it overestimates P critical, it cannot predict if we take some variations like this. We cannot really make sure what's happened. So experimentally, the degree of polymerization is only 26. It doesn't need to be infinite. Okay. If we see here, degree of polymerization is around this, 26, around 26 here. Okay. So it doesn't need to be going to be infinite. So if we take this viscosity, it's going to infinite. Right? It's supposed to be end here, okay, at our experiment. But in the theory, using the gelation theory, it seems like that. So also the problem is the distributions. Okay? But I think one simple statement, I think this the first one here. The gelation theory is simple, but sometimes it's overestimate the P critical. Okay? So if we maybe have a variation in components, the monomer, maybe the condition is a little bit complicated, maybe this gelation theory is not work anymore. Okay? So it's work when you have a simple and basic environment, not really having any issues whatsoever. So we can take the gelation theory. But if not, like if it's complex, complicated monomers, then we are not really sure on the theory, okay? Because it seems that our assumptions from the theory is not work on this experiment. Okay? Okay. So we have the definition of the network polymers, the nonlinear, okay, and then some of the examples, the silicons, right, the formaldehyde resins, the bakelite, epoxy resin, the polyurethane, and then the gelation theory. Okay. And we have two more sections, or at least one more sections to end our lecture for today's course. Next week is holiday, right? It's April, right? Oh yeah, 27, now 27. Yeah. I almost forgot the calendars. So hopefully after 2 weeks, we move to the new chapter. Okay, new chapter. And after new chapter finish, prepare to have an exam. And for this week, Thursday, we will have the discussion problem. Okay, I will give you some assignment. And please remember all the assignment from the first one, second one, and then like later the third one. Because probably I will ask something in the midterm. Basically, just my general feedback to all of you. I think you did a good job, but my point is, if there are questions asking the maybe reactions or synthesis of some polymers, maybe you need to provide some example. Maybe how the structure. If you feel maybe difficult to find in the or difficult to copy the picture, maybe it's blurred. You can just make out from books or from the website. Just use your pen, take photo, and put into your works. I think that's also okay. I think if you find, like I said before, the macro galleria, find a 3D model or 2D models, you will provide all the models for free. For free. When I learn biochemistry, I'm using one software that's also free, but I forgot the name of the software. It's typically updated the database of the polymers, so it has a huge database of the polymers. So whenever you need to find some polymers inside, maybe if it's new, maybe it doesn't have, but you need to check their banks and then put your name, the polymers, to download the one that you are looking for. It has like maybe millions, because it has variations in each type. I forgot the name. The program. Okay, now after this gelation theory, we have some additional sections on dendrimers. Okay, so what's the importance in dendrimers? Okay, if we see the dendrimers, that's the picture. Okay, so it's branch molecules. It's dense. Okay, dense with some voids here. So if you see that this is a molecules, okay, it says it's branches. So each branch has another branch. Okay, each branch has another branch, and it has the symmetric skeletal geometry, and it has also unique molar mass. Okay, and then dendrimers, if we see in more details, like 1, 2, 3 is, we call this 1, 2, 3 as the generations. Okay, which means generation is how it's going to move away from the core. So this is the core, the initial one. This has branch here, 1, and then 2. This means this layer 2. Okay. So if we take the circle, you see this is layer 1, layer 2, layer 3. Okay. So the more it has more branch, it has more layers. Okay. Okay. So this is an example of the dendrimer. No need to write this down. You can just take photos if you want. It's the polymethyl. I forgot the name. Polyamidoamine. Oh yeah, yeah. It has this amido amine. Okay, amido amine. So it's example on how the divergent detrimer, it's synthesized a bifunctional branching is created from the inactive monofunctional group, okay, from this the core, okay, and it has this we call the divergent dendrimer. Divergent means it's going to spread out. Okay, if you remember, divergent in calculus means the infinity, right? It goes to like really branch out. Okay. So this is one example how to synthesis, but I think I don't have time to tell you this. But what I do know is, first, if you see this part here, the idea is to link the core molecule to the branch. Okay, so link the branch unit become this, and then all the branch link again with another one. Okay, so it's add more layers, right? And more layers. So this is the core, this is layer and then layer, just branch and branch again, and then the surface activate again to link with another branch. Okay, so that's the idea, to make this more branch and then maybe making more layers. Okay? And we can also make, so before it's just so if you see the difference, this is having the core molecule has 3 branch unit. Okay? If we have only one branch like this, then if you imagine how it looks like, so the branch has another branch, okay? Has another branch again here, and then has another branch again. So it goes away, and then the other part is just as it is, right? So it goes away like that. So what will happen? Later we're going to see the conclusions. So another way also to set up this dendrimer, we could have, this is the core, take the branch going here, the branch going here, and then all the branch having another branch like this, okay, making this. And then you can imagine if you take another branch like another into the previous branch. Okay. So we can have a lot of branch, and it seems that it's only dense in one part, right? So what's this dendrimers do? Okay? And what is the consequences to our gelation? Okay? So these dendrimers, okay, it will suppress our gelation. So it will stop the gelation, or it will take slowly, the gelation will take slowly for this dendrimers or hyperbranch polymers. Okay. So if we take this A, B, E, okay, so one functional group A, 2 functional group B, will gelation occurs? Okay. If you think in terms of dendrimers before, like we have like branch and branch and branch, suppose that we are going to take this self-condensed, okay? Consider this is self-condensed. So we are going to take into another A, B, B, and then another A, B, B, and then another A, another B, okay, another A. And think on yourself. Think, can this connect becoming a network polymer? Imagine we take another A, B, and then it will not stop, right? So it will go over there infinite amount. So the gelation will never occur. The network will never occur, right? So network is not occurred. So it's going to be like this. So gelation will be suppressed because of too much B. Okay, you can say too much B if this is difficult to write. Too much B functional groups. Okay. So because too much B, then we are basically saying we suppress the process. Okay. Okay, I think we'll stop here. There are some few sections, but I think I will make it into another lecture later. And before we end, just a small feedback. Small feedback. Just a small feedback. Okay, I hope everyone can join. Okay, everyone ready? Write your student ID, okay? Student ID. If you haven't joined, you can go to that website, menti.com, and use the number. Oh, why now 6? Okay, 7. Okay, I think we can start. Just 2 short questions, like within a few seconds. Okay. Okay, I think it's too easy. Okay. Okay, good. Okay, one more questions. Okay, 8 players. Okay, get ready. I think too easy also, right? Oh, really? Really? Oh, everyone has voted. Oh, yeah. Yeah. Good. Remember, chain mobility in network, it cannot move because it's already connected to each other. Okay? So it's not easy, and also not having any flexibility. Okay, book. Congratulations. Okay, last one. Just write ID, and if you have any suggestions. Well, I think we are not really focusing too much on the reaction synthesis, but the basis you need to know. Okay? You need to know. Because there are many reactions. Just focus on the one that I draw. Okay, I think that's all for today. So see you next.